The goal of this lab is to compare the predictions of a constructed model of the motion of a falling object using Newton's second law with observations from an experiment. Newton's second law states that in a short time interval delta t, the change in velocity of a moving object is given by the equation shown here, where F net over m is the ratio of the net force to the mass of the moving object. Here is the experiment I performed. I dropped a yellow origami ball from a starting position at rest. The ball was of mass 2 grams. The height of one of the features on the white wooden door shown was used to calibrate the length scale in the video. The coordinate system was chosen with the origin at the center of the ball held at rest before it was dropped. The y-axis was oriented so that the object moved in the negative y direction as it fell. I obtained position versus time data from tracker, as I will show you here. I then modeled the effect of gravity alone on the motion of the falling object. To model the effect of gravity alone, we assume that the weight force is the only force acting on the object, so the net force equals W, which equals mass times the gravitational constant, which equals the weight force alone. Here is my Python code to model the effect of gravity alone on the falling object. Initial conditions I set was the initial position to the origin, initial velocity 0 because the object was dropped from rest, and set the value of g to 9.8, defined of j hat vector to choose up as the direction of the positive y-axis. To look at the motion predictions using Newton's second law repeatedly, the total time set is same as that from the tracker observations to 0.868 seconds. This while loop repeatedly calculates the value of the ball's velocity and the net force by using Newton's second law as shown in this equation. Here is the Python output when I ran the program. The yellow arrow is showing the direction of the weight force downwards, and the graph produced by Python is the position versus time graph for the situation with gravity alone. I then modeled the effect of gravity and drag force both on the motion of the object. To model the effect of drag force, I considered the drag force proportional to the square of the speed of the falling object. The red and yellow arrows that will show up in the output window of Python represent the drag force and weight force respectively in the visualization window. The following screen will show you my code. The main difference between the gravity-only model and this model is that the way we have defined F net in this program is it is the sum of the effect of the weight force and the drag force. The drag force has been defined over here as the product of the drag coefficient negative b times the square of the magnitude of the velocity, which is nothing but the speed, in the direction opposite to the direction of the motion, defined by the unit vector v hat equal to norm ball.vel by the Python function. When I run this program, this is the output I see. The yellow arrow again representing the downward weight force, and very soon you will see a red arrow going in the motion opposite direction to motion, pointing upwards, showing the drag force. This is the position versus time graph produced by Python. I then prepared a graph using a spreadsheet program by importing all the data output by Python and compared it with the observations. Position versus time graph for the falling origami paper ball is shown here for all the three different situations. The experimental data has been plotted in blue. The gravity-only model has been shown with a red line, which obviously shows that the final position is way beyond the actual observed position. This indicates the presence of another force that we might not have taken care of that creates this blue final position in reality in the experiment. So then we use the output from the gravity and drag model which considers the effect of air resistance on the falling object and predicts output positions pretty close to the observed positions. The final position of the drag and gravity model is exactly same as that in the experiment, because we fit the value of the drag coefficient b to our observed position by using an empirical approach by trial and error in the Python program, assigning different values to b until we got the same final position as the experiment. What does terminal velocity mean? As the falling object gains speed, drag force increases, becoming large enough to balance the force of gravity, making the net force zero. The object stops accelerating and attains terminal velocity at which it continues to travel. But if the object hits the ground while still accelerating, as in my experiment, it will not attain terminal velocity. This is the reason that my model did not output the printed value of the terminal velocity as per the if statement that I inserted inside the while loop of the program code as follows. My fellow peers who would be assessing my project can see the actual code as part of the submission process. If the object is thrown instead of being dropped from rest, I model this by assigning an initial velocity of -2 meters per second. The velocity versus time graphs for both the models under this condition are shown in the graph that will follow. I used the model where V terminal is derived by setting the weight force equal to the drag force. And we can observe from this formula derived here that the terminal velocity does not depend on the magnitude of the initial velocity as seen. It will be same for this model regardless of how the object starts its motion, dropped from rest or thrown downward. Here is the velocity versus time graphs for all the different models. Velocity predicted by model with gravity only in blue, velocity predicted by model for gravity and drag in red. The yellow one shows gravity only when the ball is thrown versus dropped from rest, and the green graph shows the predicted velocity for gravity and drag model when the ball is thrown. In both models where the ball was thrown as well as dropped from rest under the effect of gravity alone, we see the overprediction of final position by the models, making us realize the presence of another interaction of the object with its surroundings. The model with drag force included was able to closely predict the observed positions and the times shortly after the start of the motion. This model can be used to predict the motion of a falling object under the influence of gravity and air resistance, provided it is dropped from a much larger height than the experiment. This will help study the effect of terminal velocity on the motion of the falling object.